All right. So let's go ahead and screen share. Minimize all the nonsense and get into the part. Doesn't really matter where we're saving this today. All right. So we've got ourselves a new part file. You guys should be able to see everything now. What we're using as a reference point is we're using, we're going to use this PDF that we have attached to, it'll be attached to the announcements for this week as well. But this will give you a pretty reasonable starting point. So a broken out section is what this is talking about. It's one we haven't really done a lot of, because occasionally you'll have to insert a view that explains what's going on with a part, and that's what that is, a broken out section view. All right, so the assembly that we're actually going to be making is this one. We have just enough information to be able to make or recreate the entire part, and you might be tasked to do something like this on the CSWA exam. So this is another really, really good example of how to do it. They do include a variable. It looks like a lot of you had already gotten to the design tables and things, so that's a good start, but we want to make sure that we're including this. This is another really, really good part example, and then I'm going to dump a whole stack of files on you guys here in the coming weeks so that you're drilling constantly, because I think that'll really, really help get everything solidified for you. It'll make things a little easier to kind of keep up with and see. So they give a thickness, and they give a couple of variables. In this one, yeah, they even specify what the bracket gap is between those. They specify the material. The pins are 5mm in length and diameter. So all of the information, even though you don't necessarily have 100% of everything, all of the information is here. So we want to start breaking down what information is there. First piece we're going to make is the pin, because that'll be pretty quick. So 5mm, equal length and diameter. So we're going to start a sketch. This one, sure, top plane. This part's going to be pretty quick and easy. 2.5, and then extrude to 5mm. So 5mm in diameter, 5mm in thickness. This gives us our pin, so we're going to save that part. We need to save parts in order to drop them into an assembly and get everything oriented correctly. So we're going to go ahead and do that, because that's going to be, I think, a really helpful example for you guys as well. Something that you can come back and reference, since we've covered kind of the majority of the techniques now. What I'm going to do is all right, we're going to do one more part, and we're going to create this L bracket. Now, there's always the question, where do we start on a part like this? Can be a tricky question. or it can be very simple. So let's see in the chat, what do you guys think? Do you start from the side profile and then do sketches and cuts? Do you do from the bottom profile? Do you do from the side profile and extrude out? What do you guys think? What is the most efficient way to do this? Let's see what the votes look like. Like side as in you try and capture the L here. Do you do a front extrude and you extrude this part? Because you can do it with a lot of sketches or you can do it with a few sketches. The side profile will get you most of it. That's true. Yes, the 3D printing file you want to send to me as an STL either through messages or as an email attachment, either one of those. All right, so definitely you want to capture the most of the things that you can in a single sketch. And remember that we can come back in and do filleting at the end of all of the operations that we're doing. So we know a couple things, one of which is this bracket is symmetrical. So we know that it's 20 millimeters wide. We know it's 30 millimeters on the side. We know that it's also going to be 30 millimeters in height. Part of why we know that is we have 20 millimeters here. We have a 10 millimeter hole, and here we have a 5 millimeter gap. So half of that distance is 20 and 5 is 25. The remainder is about 5 because this is a radius of 3. So we know for sure by inspection that the total height, it's a 30 by 30 rectangle. So you can do it that way. But there's another way that you can do this as well. So in keeping with the way that I've been training you guys, the most efficient is going to be, let's make the 30 by 30 rectangle and then do some holes and fillets because this is a pretty quick shape to make. So we'll do right plane for this one. And we're going to have one rectangle going up like this, another rectangle going up like this. We want to make sure the total is 30. Make sure the total is 30. We trim out this little section that we don't need here. All right, we can do a little sketch filleting because we know that that's going to be the case. We know this one back here has a radius of 3. So we know that one has a radius of 3. We want to check this interior. We also have some radii. This one isn't necessarily real obvious, but we have a thickness of 2. So if we have a matched radius on the inside, what do you guys bet? Let's see a vote in the chat. What do you guys bet the radius is on this interior? The outside is radius of 3. We have a thickness of 2. We know they're using a 1 radius on all these other corners. What do you guys think the inner radius here is going to be? What do you guys think? What would be the most reasonable? And then we'll show you why. I see a vote for 1. Anyone think it should be maybe 2 there because it should be less than 3? I'll show you guys a quick rule of thumb. This radius, if it's 3, what it's going to do is it's not going to be part of the same arc, basically. So instead, we're going to do the first fillet, then we're going to do the second fillet, except 3 minus 2 is a radius of 1, and that maintains a thickness of 2 all the way across. You see that? So it's a uniform thickness, much in the way an actual stamped part is. So radius of 3, radius of 1, so radius outer minus the thickness of the part should give you the inner radius, gives you something to aim for as you're working along trying to develop parts like this. So this is all we can do at the moment from this angle. So we're done with sketch fillets. We go ahead and extrude by 20 millimeters. And we make sure that whole contour is selected. Okay. We can do the radius on all of these corners, but you want to wait a little bit before you go doing those. So first thing you want to do is add one more sketch. You want it to be on that front face, so it should automatically center. And you're going to add a center line, and you're going to reference the center of that top line. You're going to add another center line. Okay, this needs to be 10 millimeters in. This is already at the center. I'm going to reference that anyway. 10 millimeters, 5 millimeter diameter circle to give us our 10 millimeter hole. And on this top part, we need to do that cutout as well. So we have a rectangle that comes over here to the edge and does something like this. So we know that depth needs to be 5 millimeters. And we know this depth needs to be 5 millimeters. And this height needs to be 20. So now we have our 10 millimeter pitch for a 10 millimeter diameter hole. We have our 5 by, actually, this is 4 deep. So I need to make this adjustment. 4 millimeter deep. So 4 millimeter deep hole punch on the one corner, and that'll sit just at the right height up above. So we can do our extrude cuts for those 2 sections. Okay, punch those out. Now we need the same thing for the circle on this one. Center lines are really helpful for getting you there. And you could do this once you have the center line referenced. You could do it without using the horizontal reference line, but I don't recommend it, so that you know for sure where you have it placed. You want to zoom in and not associate it with that point. All right, extrude cut. All right. Okay. So we have our part. So this looks remarkably like what we're supposed to have here, except we need to do those radii for those fillets. So each of these corners needs to be 1 millimeter sure to show preview. There we go. So we've got our 1 millimeter radius fillets at all the corners, and now we have our stamped part. And what we're trying to reference here is we're trying to reference the starting point for how we get our assembly put together. So some of the things we haven't necessarily covered is how to put together some of these slightly more complex assemblies. So these are things that we're going to need coming into the following weeks, because there's a lot of assignments coming up with assemblies. We're going to be building the 4-wheel drive cars, so we're going to introduce all this very soon. We want to make sure that we're drilling on techniques, so that when you guys go to do the CSWA, we have a really high pass rate, because that's ultimately the important metric for you guys to be able to take something away from this class, right? It's less about a grade and more about getting a certification that you can carry with you to help you more easily land a job. So we've got all of our details there. Now we're going to save this as the L bracket. Then we're going to start building the assembly. So we haven't done assemblies for a little while. So make assembly from part under file is where we go. And as soon as it gets all caught up here, this laptop is not bad, but it's definitely not a desktop. So we need some of the pins. Aha! See, we're going to have to go back and make some edits to the pin, because that aspect ratio is wrong. So some of you are wondering, what in the heck is he talking about with that aspect ratio? What is this business? Incorrect aspect ratio means very tall and thin versus very wide and short. So the aspect is all wrong for that part. So I'm going to go ahead and put in some of those pins. There's a couple ways that you can move component. You can make copies and some other things. There's lots of options that you can do. But for now, I'm going to go ahead and insert the other pins that I need. So I need a total of 3. Then I'm going to go back and edit those. I'm going to do 2 more brackets. And then once everything is in place, I'll worry about the way this is set up. So we're going to go back and make some edits, because we've still got the pin open. So we're going to edit that base sketch, because not the actual feature, but we're going to edit the base sketch. So that came out with a diameter of 5, which it should have had a radius of 5. Diameter needs to be 10 to match. So now, when we look, we have the correct aspect ratio. So width to height is an aspect ratio. That's the thing that a lot of you have lost points on when your dimensions are hugely inaccurate. There's a big difference between how this looks and how that other pin looks. So now we go back to the assembly. Yes, we update the parts. All right, so now these clearly match. A couple things about mates in the assemblies. Often you want to select a mate first. And a little bit of kind of quick background for this. These parts can be freely moved, but you will notice one of them cannot be, usually the first one you place. You right click. You can float or fix something. So this one is floated. All the rest of the components are floated after the first one that you position. So you need to pay attention to how that works. And this is a very, very important aspect of all kinds of assemblies when you go to manipulate them, is understanding which part is fixed and how that's going to change, because a floated part has all the degrees of freedom and can do all sorts of wonky things while you're trying to put together an assembly. So we need to reference which part of which one goes where. So the notched part goes to gets mated with a part that has no notch, and that's something that we want to pay attention to as we go to put the assembly together. So the first one is roughly positioned correctly. So what we need is we want to select a mate. Usually we want to know what we're selecting before we actually start selecting parts. There's reasons for that. We'll get into more about why later. So we need this and this cylinder to be concentric. You don't need to lock rotation for this. That creates extra constraints later and creates some problems. So you hit OK. Then you can add one more where you do a coincident between this top face and this face. Concentric and coincident are a very helpful pairing for a lot of reasons. Now that will mean this is fixed. It can still rotate. Won't really be able to see that. But we're going to do one more that's going to be concentric. Again, I want you guys to get in the habit of picking the mate first and then picking what it's going to be mated to. So here you have an option to change the mate alignment, and you can change to a parallel or an anti-alignment. In this case, a parallel alignment makes sense. Functionally, it behaves as an anti-alignment for us, but the intricacies there are not super duper important. So then you can set a distance mate based on the information that they gave us, right? Remember, there's a 1 millimeter gap between the brackets. So this L is a 1 millimeter gap. So that means we need to do now a distance mate of 1 millimeter between this face and this face. And it needs to be 1 millimeter. And I'm going to double check that that pin dimension is actually correct, because this should be, I'm going to go back and check the base part, because I think we actually have a thicker extrusion width than what is called for. We should have 2 millimeters. So based on there being a gap here, that tells me this extrusion width is actually closer to 3 and not 2. So I'm going to go back to that part, the L brackets, and I'm going to double check the dimensions on this. Yep, that's not specified. There we go, 2.5. That's why. Needs to be 2. Needs to be 2. All right. So now that is correct as far as thickness and aspect ratio. You want to resave when you make an edit to that base part. Always resave. Now we'll have what looks to be the correct thickness for the stamped part. When you go back to the assembly, it'll reload correctly. Now that 1 millimeter gap lines up and everything is flush as it should be. So that extra 1 millimeter showed up as a problem. Now you'll note this piece still can't move, but this piece can rotate freely. So we can position that close to how we want it. And then, but you can't move it vertically or horizontally. Its only degree of freedom left is rotational, which is okay. So they're going to specify an angle. These can be a little bit tricky, so you want to pay attention. But the 45-degree angle between this edge and this edge is what's being specified here. So we're going to use a mate. We're not going to use smart dimension when we're doing, typically when we're doing assemblies. Smart dimensioning happens in the sketches. Assemblies are a little bit different. So this flat face and the reference of this face, 45 degrees. So two faces, two edges work really well together. And then that will be fixed. This can no longer rotate and move anywhere because it's now axially constrained for all three dimensions. So same kind of thing. We're now going to take this, make it concentric with this, and we hit OK. We're going to add one more to be coincident between that bottom face and this face. So now we're set up to get our alignment. We may actually not need the third pin. Yeah, we don't need the third pin, only the second one. And then we'll set this with a 45-degree angle. So this one is going to get a concentric to this. You can also make it concentric to the edge, but that'll create some additional headache that you don't necessarily want. Then coincident between this face and this face will leave us our 1 millimeter gap, as it should. And then you'll notice this can still freely rotate. So we want this now to be set at the determined angle of 45. So we're going to set an angle, and we're going to set it at 45 between that face and this face. Now the interesting thing is, you see where this anti and parallel alignment comes into place, because that's 45 degrees from the opposite reference point, and there's 45 from, yet again, the opposite reference point. And so regardless of which one of these two you choose, it's not going to work out that way. So somebody that's good at math, tell me, how do we fix this? Anybody remember back to their trigonometry days? Sure, a few of you will be triggered just hearing the name. What angle do we actually specify? What do you guys think? In order to actually get an effective 45 degrees, what do we have to do there? Any ideas? If we need an angle of 45, but we can't specify that 45 is the correct angle, we do anti-parallel. So we can't just switch it. There's no quick fix. So what's the actual angle that we put in there if we need 45 degrees? This is the kind of stuff that the reason we're going over this is you guys take the exam and then get stuck and go, it's 45, it's not working, I don't know what to do. That's why we're trying to run into this stuff beforehand so you know exactly what to do. Try this trick. Change the reference point. 45 plus 90, because of orientation, 135 degrees gives you your actual gives you your actual 45 degree reference without needing anything else. So we're going to delete the extra part. All right. So we need to set our materials, but we're going to have to set those in the material, in the parts themselves. So they want titanium. So in order to change material, you have to go back here to the part for both of them. Under other metals, titanium, apply. So we save. Same thing with the pin. We're not actually trying to configure materials. We're not building them from scratch. So we apply titanium as a material. Save it. Now we have our automatically updated assembly. And the last thing we need to do is, based on this, we need to figure out what is the center of mass. So they're not asking actually what the mass is of the part, but they're asking center of mass based on coordinate system y, z, and x. So we'll have to check the orientation. So the origin is somewhere up here, so that's not going to work. So instead, the origin is going to have to be down here at this corner. It's going to be a little tricky to orient, but it'll make sense in a second. So we need to insert a reference. So under assembly, reference is up here, a coordinate system. So we need it to be basically at this corner, in as much as is possible. Because it's rounded, it's a little bit nebulous. So we're going to put it right here at the base. Now we have to pay attention to what orientation it is, because the red is X, the blue is positive Y, or blue is positive Z, green is positive Y. But in our reference, Y is going up, X is going backward into the part, positive X, and Z is going, positive Z is going along the front edge. So this whole reference system needs to rotate by 90 degrees. So I'm not going to define as positions, but I'm going to rotate, and it needs to rotate around the y-axis by 90 degrees. So it should give me the preview still. There we go. So this now has Y pointing up. The blue, the Z, is pointing along that front edge, and the positive X is pointing backwards into the part. So we have a reference coordinate system, and we're going to be able to get the center of mass that is closest. So we're going to look at evaluate mass properties and compare that to our options. So center of mass minus 7.31 y. So x should be minus 7.31, y should be minus 6.3, z should be minus 4. So this is a much different reference point based on this, and I think this is part of the reason why they got rid of this particular question, because this is dimensionally exact. However, this is with our default coordinate system. There we go. So because of that curvature and some of the confusion that introduces, roughly 40 for X, roughly 24 for Y, and 20.5 for Z. It's not an effective strategy to just pick whatever one seems to be an oddball from the group of answers. That's not going to get you to pass the exam. You always want to make sure you're referencing the correct coordinate system, because that makes all the difference. It's very clearly not any of the other three. It's very clearly this one, but their reference coordinate system is adjusted slightly, probably out at this corner. So you would have to do reference lines and a reference point out in space to get it to be exact. That's one of the reasons why this particular question is no longer there. Is there's enough inaccuracy to create some problems. All right. Questions on this first one? The bracket is definitely titanium, but the reference coordinate system is enough to make very large errors in an assembly like this. So that's part of the reason why we're hammering on some of those principles. Because the thing is, the assemblies are actually the majority of the actual points on these exams. They're really, really tricky. So you want to make sure to have as many of those included as possible. You want to make sure to get the assemblies done first, because they're worth more points, and then go back and do the parts. And then the concept questions are just a handful of the points. So the smart among you will be hearing that I am telling you exactly how to pass the exam very quickly and efficiently. You just have to pay attention to the details. Understand what they're testing and how to take the test correctly. In the question, for the bracket, yeah, it does say 6061, actually. So that one, and then the pin material, titanium. So let's change that, and I'll take a quick screen grab of what this difference is. The material will make a slight difference, but it'll be good for you to see exactly what that is. Because yeah, if they do use two different materials, that's another kind of gotcha that they'll sometimes put into it. So I'll look at the mass properties. We'll take a snip of that. All right, so let's update the L bracket to be 6061 aluminum. They have real similar actual densities, so this will be a good example of why, yeah, 6061 alloy, close. All right, so if we save that, you also have to make sure that you save the part, because otherwise the assembly won't actually update. So if we look under mass properties again, I'm going to reload this. So you'll see the reason I wasn't particularly hung up on the details there. I get those side by side. So the center of mass with those updated materials is the same. The overall mass is the same. I recognize that seems a little bit hard to believe, but you can see that the material has updated. So just to verify, these are now showing a 6061 alloy. And if we reload mass properties again, we are the same as what we were. Looks like that snip went away. Yeah, so it's still a 39.23. So even though that seems like that could make a huge difference, titanium is very lightweight, 6061 is very lightweight and strong. Their mass densities are pretty close. and that's why people like titanium. You get the weight and density more or less of aluminum, but with the strength as good or better than steel, and that's why it's kind of a prized metal for engineering. Really cool the way that works. But yeah, that's what we're looking for, is we're looking specifically for all of those kinds of little details, double checking. Oh yeah, they actually said, wrought iron. That's going to be hugely different, right? So if we update that material, it would be a totally different mass density, totally different value. So let's verify that real quick. Make sure SolidWorks isn't just horribly broken. So yeah, something like gray cast iron. So then save this.
Okay, new vision. So.
All right. Now we go back to the assembly. Let's check under evaluate mass properties. So it's still saying, perhaps because these are so small, the mass differences are not showing up as tremendous. They should shift slightly. That's still showing the same approximate mass and center of mass, which is interesting. So again, that's another reason probably why they didn't change it, is because you could make all of those sorts of mistakes and the program wouldn't necessarily pick up on all of those, because they're so much smaller, really small stamped pieces. You're not saving weight tremendously over something else, because it's still displaying now as cast iron. So they should have differences, but it appears they're not big enough to really register. So the more you know. That's why it's important to pay attention to some of those kinds of details. All right, so there's one more part, and in this one, so we've already done this one, this part. So this one, you do have all of the knowledge, question 6, you do have all of the knowledge in order to actually do this. What I want from you guys is to go ahead and give question 6 a try. So go ahead and get started, and then let me know where you're actually getting stuck. So I'll pause the recording here and then pick up where we actually follow up here, because there's a lot of stuff going on for this part, but you really only need the one view here, the isometric view, to generate the entire part and check that the answer is valid. So we're going to give you a little time to start working on this. And this will be more like some of the classes going forward. They'll look a little bit more like this. So I'm curious to see what you guys can come up with. All right, guys, we're going to do a redo of this first one. We had a failure of the actual recording for the second part that we were making. So what we're recreating is this part here. You're fine. You're recreating this part here. And what this is going to do is we're going to create it from the side profile. So there's a few key parameters, 40 millimeters, 25 on one side. Then we're going to create these lower feet and all the rest. A is 100 millimeters for this one. So then we're going to do some reference planes for these two. And there's an easy way to do that so that we can rip through it really quickly. So this is what we'll do to recreate this. So what we do is we start off with a sketch here, corner rectangle, and we're going to have a couple smaller rectangles down here. We're going to have another rectangle here to give us a reference point. Okay, and that whole length is 100. This will be our 40. This will be 25.
The time is.
So what we need is 40 millimeters, 25 millimeters. This is actually 200 millimeters down here. 200. This separation distance, we need to be 60 from that top dimension right here. So 60. And then we're going to have a center line at the base. So we're going to adjust these. So 50 millimeters in, 37.5 millimeters, 37.5, and 50.
Billy was
25 millimeters, 37.5,
I don't know. You first do.
and
So then you have 9 and 10.
10.
So you're now in 2 sides.
Okay, 10 and 10. And at that center line, we're going to have a reference.
Mountains,
So all the way up.
Oklahoma.
This is going to connect at the top.
On
Okay. I'm going to trim out this piece, which we don't need. These pieces, which we don't need. We need
here,
12.5.
Illinois.
Anchor this so that our reference point will be an arc.
Now I'm setting, right? Plus. Which is what you always have. Right? So,
Smart dimension.
let's see.
Smart dimension here. Radius of
And then
50.
Those are mountains, Oklahoma. On an Indian road. Bullet point out if you want to.
And we need this whole distance to be 60. So now we should have a correct reference point for our radius of 50. And then we have all the pieces that we need to be able to do the extrude from the side. So let's go ahead and do that. So extrude
Because right now you're writing 7.
this section and this section, as well as these two. We're going to flip direction and go 30 millimeters, which is this thickness. So 30 millimeters. Okay. So we've got our first part. We're going to do the next extrusion. We're going to do from that same sketch where we go all of these pieces the other direction, 70 millimeters with offset of 30, flip the offset. So now we have 70. So this is the majority of what we need here. So we've got all of these features. Now we set up our sketches. We've got 2 more to add real quick. So maybe add another sketch on this base.
So right here.
This is a reference center line, which we're going to set the angle between here and here to be 20 degrees. So now we have a sketch reference. What we can do is add a reference plane. So we can reference this edge, this point, and this point. Usually that's enough. I'm going to go ahead and clear the references. So sometimes it's enough to reference one line and a line on the edge. For this next one, that's going to be a little more nebulous. We'll have to do it. We'll do it a little bit more. We'll do it a little bit differently. So I'm going to change my orientation here. I'm going to do a sketch, and I'm going to reorient. So it's not going to be a sketch on plane one. It's actually going to be a sketch. Let's see. It'll be a sketch here on this plane. And we're going to create a reference line there. So we're going to step out. We're also going to create a reference sketch on this side. So we're going to reorient our view. We know the distance needs to be 100 from here to here.
We can pay this project.
And let's add a center line. So between this line and this arc should be a 30-degree arc. So now step out of the sketch, add the reference. This time we're going to have to reference these two planes, this and an angle of 30 degrees and another reference point here. This allows us to get all of the pieces that we need in order to make this plane a workable reference. So this, I can now create a sketch across in a line. So on this plane, we're going to create a sketch. So this one's a little more complicated. So we're going to do
red,
we set our view orientation here.
and tomorrow we will have notes on the here. So
This needs to be 70, and I'm going to set the distance. I'm going to zoom in, set the distance between this and this edge to be 0, and we set up our reference rectangle. So here we have 70 by 50, 50, 70. There we go, 70. Okay. And then we get our 3-point arc starting from the center. All right. Then we have our 2 radii. So the inner for this one, the inner is 15, the outer is 25 with a depth of 5 millimeters.
You're talking about on squatter. People would find places right away.
25.
They make a home of anything.
15. Then we had one more thing we're going to need here, which is going to be a center line. Because we need that center line to give us the reference for the center point rectangles that are going to be the easiest way to represent this sort of cross-shaped geometry.
I think we're gonna have stop with that.
So this okay, same deal on this side. And same deal here. Use our smart dimensions. 10. And 10.
Okay, so they're still going over
10.
and then
All right. And we come in and do some trimming. So we don't need these in here. All of these can go away. And we can do okay.
Yeah, that's what
All right, we've got all of those deleted. These small arcs aren't necessary, so we cut out those segments. Same deal up here. And so we've got those pieces, and we've now got enough to create this part. So we go to extrude. This one, we're going to have to flip the direction. So that we're going the opposite direction. And instead of blind, you're going to do up to surface. And there's 2 surfaces we need to go up to. And face 1 and 2 are those. Now we have this piece. We do our extrude cut based on our previous sketch. We do an extrude cut of those 5 millimeters deep.
You know,
5 millimeters deep, and then we do one more. We do an extrude cut from the sketch plane through all, because they tell us that all holes are through all. So the only other ones that aren't through all are these 5 millimeter depth cuts here, but now we have our through all cut for the first one. So now all we have to do is solve this part, which then becomes, we're going to do a sketch on plane 1. So that's not on plane 1. We're going to create a new sketch. You have to make sure it's actually on the plane that you think it is. Otherwise, you'll create all sorts of headache. So we go back to corner rectangle. And we get our dimensions here. So 40 high, 50 wide with a 15 millimeter pitch. So, here we go. So 40 high, 50 wide. 50 wide. 40 high. Okay, got our arch. We want to do 2. Then our dimensions are 12 and 25 with a 15 millimeter extrusion. So we'll see how to do that. 12, 25. So 12 diameter, 25 diameter, 15 millimeter extrusion up from the surface. So 15 millimeters blind extrusion,
Yes, you can use the other one.
15 millimeter blind extrusion up. We're now going to do the second extrusion into the base. And so we do these and these two. So all of that surface, we're going to flip direction and we're going to do up to surface, which is this base. So we've now got our piece and we have to make this a through all hole with the last extrude cut. So nothing too extreme. And then through all cut. So we've got a through all cut. Now we change the material. So this is supposed to be a 6061 alloy. 6061 is one of the aluminum variants. 6061 alloy. We apply that, and then we look at mass properties. And we see 241.94 grams. And we see the closest to that is this 240.57. So we're within the 1% we need to be for this. And that's the quickest way to recreate a part like this. There might be minor differences in the part, like the extrusion angle here or some of the other things. The particularities of the cut here are something that could make a gram worth of difference very easily in a 2,000 gram part. So things that we want to keep in mind, but by and large, this is going to give you exactly what you're looking for. So this will give you enough that you can work on recreating a lot of the parts like this with confidence, so that it's not just a high stress situation. This is only a handful of minutes long in terms of recording. So these are parts that you should be able to generate without explanations and extra distractions in somewhere between 20 and 25 minutes in total. So that's what you want to get to. That's what you want to drill to and ultimately end up at in terms of the concentration factors and things that you need to have in order to get these done. So real straightforward, but we got to make sure we've got all the right pieces. So I'll get this all rendered into a single video. Sorry for the messed up recording. I'll go back and see what questions come up out of this. And then hopefully this is helpful in showing you the step-by-step process. No fancy keyboard shortcuts, just numbers and the enter key mostly. So the only other things are using the control and clicking with the scroll wheel. So holding control and clicking the scroll wheel allows you to move parts, zooming in and out all the time, and clicking down the scroll wheel to rotate parts. Those are the things I need to be able to do to develop parts quickly. So hopefully that's helpful. Let me know what questions you guys have, and I'll get this all rendered. Thanks.